Sir.
Good afternoon, sir.
Good afternoon, Beta. So I have started the recording of the meeting. So morning session, we discussed about circumpolar bodies. Now we are going into some other topics related to principles of navigation on which the questions come in our papers. So one by one, we will go into those topics. They are number one, stellar magnitude, then some related to Kepler's laws of planetary motion, then chart projection. So one by one we are going to cover them up.
सर एक डाउट था
बोलो बेटा.
सर जो एक्सरसाइज थी ना सर स्टार सुटेबल फॉर ऑब्जर्वेशन
राइट.
सर उसमें विजिबल नॉट विजिबल तक तो हो गया, उसके बाद जो पी निकालना है सर वो आपने बोला था वो पी डिवाइडेड बाय 15 डिग्रीज इनटू 60 मिनट्स.
राइट.
उसके बाद सर उसके बाद ये समझ नहीं आ रहा, उसके बाद एक्स मेरिडियन लिमिट है ना सर वो कहाँ से आएगी? मतलब अभी
राइट बेटा, मैं
उतना तो
समझ
मैंने
गया.
कर लिया, पी टाइम टू फ्रॉम हमारे पास निकाल लिया.
आपके पास टाइम आ गया. लेट अस से एक
Yes,
स्टार
sir.
का टाइम आपने निकाला और वो टाइम आ गया 20 मिनट्स. तो
Yes,
अब
sir.
हम कैसे पता करें कि ये स्टार एक्स मेरिडियन के लिए सूटेबल है या नहीं है? कैसे इस चीज़ को पता करें? अब हम बेटा जाएंगे नॉरिस टेबल एक्स मेरिडियन टेबल्स के अंदर. पहले टेबल 1 में जाएंगे. यूजिंग द लैटिट्यूड एंड द डेक्लिनेशन, दोनों चीज़ें हमारे पास हैं. लैटिट्यूड इज गिवन टू अस इन द क्वेश्चन. डेक्लिनेशन हमने स्टार टेबल से निकाली है हर एक स्टार की. विथ दीज वी गो इनटू टेबल ए. तो टेबल 1 में से ए की वैल्यू मिलेगी. इसके बाद टेबल 4 में जाएंगे. टेबल 4 से हमें एक्स मेरिडियन लिमिट मिलेगी.
ओके सर, ओके समझ गया सर. वो फिर आगे जो रहेगा.
देन यू कंपेयर इट विद द टाइम.
Yes.
अगर टाइम लिमिट के अंदर है तो सूटेबल, अगर टाइम लिमिट के बाहर चला गया है नॉट सूटेबल.
सर एक और
ये जो सुब्रा सर की जो एक्सरसाइज है ना सर, इसमें जो 5th क्वेश्चन है उसमें उन्होंने एक स्टार लिया नहीं है सर.
बेटा उसमें आंसर्स में काफ़ी सारी मिस्टेक्स हैं, इसीलिए मैंने आपको करने के लिए नहीं बोला था वो. सो देयर आर क्वाइट अ लॉट ऑफ मिस्टेक्स इन द बुक, इन स्पेशली इन दैट चैप्टर.
ओके सर.
सर
बोलो बेटा.
सर अगर जैसे क्वेश्चन था ऑब्जर्वर मेरिडियन जो और इन्फीरियर मेरिडियन वाले जो क्वेश्चन होते हैं सर, उसमें हमारे पास 2 एसएचए की रेंज आती हैं. सर अगर उस क्वेश्चन में कोई ये पूछ ले व्हाट स्टार्स आर सूटेबल फॉर द ऑब्जर्वेशन, तो जो एसएचए हमने लेते हैं मतलब स्टार का, वो उन दोनों का मीन करके ले ले, या मतलब सर हम जैसे माइनस करने के लिए स्टार लेते हैं ना कि एक इमेजिनरी स्टार का जो एसएचए हमने लिया, हम हमारे पास तो अभी कोई एसएच कोई फिक्स एसएचए का स्टार नहीं आता. हमारे पास रेंज आती है एक स्टार्टिंग टाइम की और एक एंडिंग टाइम की, कोई एसएचए का वो नहीं आता. तो अगर इस क्वेश्चन में अपने को वो निकालना हो कि विच स्टार्स आर सूटेबल फॉर द ऑब्जर्वेशन, जैसे हम एक्स मेरिडियन की लिमिट निकाल के सर करते थे ना, तो उसमें हमारे पास एसएचए ऑफ स्टार होता है एक, तो उसका और जो स्टार का एसएचए दोनों को माइनस कर देते थे, है ना. तो इस केस में
होल्ड, आई गॉट योर डाउट. जो ये वाले क्वेश्चंस हैं जिनमें वो हमें एक लिमिट देते हैं कि इतने बजे से लेके इतने बजे तक कौन से स्टार्स ने मेरिडियन को क्रॉस किया है, इन क्वेश्चंस में एक्स मेरिडियन की सूटेबिलिटी हमसे नहीं पूछी जा सकती. दे कैन नॉट आस्क द एक्स मेरिडियन सूटेबिलिटी इन दीज क्वेश्चंस.
ठीक है सर. वो तो सर कर रहा था ना, टेबल बना रहा था, तो टेबल में मैंने कहा कॉलम बच गया, अब इसमें कैसे फिल कर सकते हैं, इसलिए मैंने पूछ लिया सर.
इसमें एक्स मेरिडियन का सवाल बनेगा ही नहीं, और रीज़न इसका मैं बता देता हूँ आपको. आप जब एक्स मेरिडियन की सूटेबिलिटी चेक करोगे, इट कैन बी चेक्ड फॉर ए इंस्टेंट. आप बोलो जी अभी टाइम है 14:43.
वो तो सर इंस्टेंट वाला तो वो जो इक्वल टू और जो इक्वल टू आता है और ग्रेटर देन इक्वल टू वाला पॉइंट जब आएगा तब इंस्टेंट चेक किया जा सकता है ना. वो तो कि लैटिट्यूड प्लस डेक्लिनेशन वो अगर ग्रेटर देन और इक्वल टू जो होता है उसी पॉइंट पे कह रहे हैं ना सर आप.
इन क्वेश्चंस में हमें रेंज दे रखी है. अब हर एक मिनट में या हर एक सेकंड में कुछ स्टार सूटेबल हो रहे हैं, कुछ नॉट सूटेबल हो रहे हैं. सो दे कैन नॉट आस्क यू विच ऑफ देम आर सूटेबल, विच आर नॉट सूटेबल. वो सूटेबिलिटी सिर्फ पहले वाले 3 टाइप के जो क्वेश्चन हमने किए थे उनमें ही आ सकती है, इनमें नहीं आ सकती.
ठीक है सर, ठीक है सर, थैंक यू.
ओके ओके. सो चलें बेटा आगे अपने नेक्स्ट प्रेजेंटेशन.
आज सर हम वो चार्ट्स भी डिस्कस करेंगे सर, निमोनिक चार्ट्स, मर्केटर चार्ट्स,
हाँ
उनके
बेटा,
सर थ्योरी क्वेश्चन भी हैं।
मर्केटर चार्ट पे थ्योरी क्वेश्चंस आते हैं, सो आई विल डिस्कस दैट.
ओके सर।
Okay. So let's go into the presentation. I will set it up. Just give me a minute. In this presentation, we are going to learn about numerical, which are based on different concepts in celestial navigation or principles of navigation. Now, the first concept which we are going to look into is the concept of stellar magnitude. Now, we are aware stellar magnitude is basically a scale which gives us the apparent or relative brightness of different celestial bodies. Let's see the question. The question says star A has a magnitude of minus 0.8 and it is 30 times brighter than star B. Find the magnitude of star B. Now, all these questions which we are discussing are picked up from the past papers. So let us see how do we attempt this question. Now, for doing this question, we need to be aware of two things. Number one, that the stellar magnitude gives us a formula or a relationship with which we can find out how many times a particular body is brighter or dimmer than the other body. What is that formula? The number of times a star is brighter than the other is given by the formula 2.51 raised to power the difference of their magnitudes. So this is the formula which we will be using in this question. Now, second concept which we need to be aware of, which we have done in our school time, that is a logarithmic concept. That formula, logarithmic formula, is log of a raised to power b is equal to b multiplied by log of a. So this is a logarithmic formula which we will be using, which we need to use to solve this particular question. So once we are aware of these two things, the question can now be solved. First of all, let's assume that the difference of magnitudes between the two bodies is x. If the difference of magnitude between the two stars, star A and star B, is x, that tells us 2.51 raised to power x should be equal to how many times one star is brighter than the other. Now this is given to us in the question. The question says that star A is 30 times brighter than star B. So this tells us 2.51 raised to power x is equal to 30. Now we want to solve this relationship for x. So for this, what we do is we take a log on both the sides. So this gives us log of 2.51 raised to power x is equal to log of 30. Now applying the logarithmic formula which we saw, log of a raised to power b is equal to b multiplied by log a. Similarly, you see log of 2.51 raised to power x is equal to x multiplied by log of 2.51, and this is equal to log of 30. Now keeping x on one side and taking the other items on the opposite side, we get x is equal to log 30 upon log of 2.51. We can easily solve this using our scientific calculators. So when we solve this for x, it gives us the value as 3.6958. So this x, which was assumed to be the difference of magnitude between star A and B, has been found to be 3.6958. Now it is given that the magnitude of star A is minus 0.8. The difference is 3.6958. And since star B is dimmer, it is given in the question, star A is 30 times brighter than star B. So this tells us that the star B is a dimmer star. Now, since it is dimmer or less bright, its magnitude number will be greater than the magnitude number of A. We know that the stellar magnitude scale is a reverse logarithmic scale. That means as the brightness increases, the magnitude decreases. And as the brightness goes down, the magnitude number increases. So this tells us that star B, which is dimmer, its magnitude number should be greater than the magnitude of A. So magnitude of A was minus 0.8. The difference between the two is 3.6958. This is the difference between magnitudes of A and B, and magnitude of B has to be greater than the magnitude of A. So what we do is we add this difference 3.6958 to the magnitude of A, which is minus 0.8, giving us a value of 2.8958. So this is the magnitude of star B. Is it clear, beta? Any doubt in the solution?
सर अगर बोला होता कि B is brighter than A, then
ओके अगर ये बोला होता कि B is brighter than A, तो इसका मतलब है कि B का मैग्नीट्यूड A के मैग्नीट्यूड से भी कम होता. सो इन दैट केस वी विल बी सब्ट्रैक्टिंग दिस डिफरेंस. तो ये हो जाएगा माइनस 0.8 minus 3.6958. So it will be a value close to 4.4 or something.
okay sir, okay.
Okay. और बेटा any more doubt? ओके ये बेटा छोटे छोटे सवाल हैं जिनमें ना अलग कॉन्सेप्ट यूज होता है. अब ये जो लॉगरिथमिक फार्मूला है log ऑफ a raised to power b is equal to b log a, ये सिर्फ इसी क्वेश्चन में यूज होता है. अदरवाइज वी डोंट यूज लॉगरिथम इन एनी ऑफ द क्वेश्चंस. इसलिए मैंने ये स्पेसिफिकली पिकअप करके आपको यहाँ पे दिखाए हैं सो दैट इफ दीज क्वेश्चंस अपीयर इन द एग्जाम्स you know what is to be done and you are able to solve them. Okay, so shall we move on to the next one, beta?
Yes sir.
Okay. So you can see now star B magnitude 2.8958, star A magnitude is minus 0.8. The difference between both of them is 3.6958. And if you use that difference in this equation, 2.51 raised to power this difference, it will give you the value of 30. So this is how the question is solved. Now moving further, the next set of questions is based on Kepler's laws of planetary motion. So there are three laws which basically give us an idea about the motion of planets around the sun in the solar system. So before we go into the numerical, let us discuss about Kepler's three laws of planetary motion. The first law of Kepler states that all the planets revolve around the sun in elliptical orbits. So as you can see, we have this blue color planet revolving around the sun in an elliptical orbit. The green color orbit which we see in the diagram is having elliptical shape. Now before Kepler, people used to believe that the orbits of planets are circular, but Kepler's with his observations proved that these orbits are not circular but elliptical. Though the ellipticity of these orbits is very, very less, they are very close to a circular shape, but still they are not exactly a circle. They are not exactly circular. They are actually elliptical. Now, just as a circle has one center, the ellipse, on the other hand, has two reference points, and these reference points are known as focus. So it has focus 1 and focus 2. In plural, it is known as foci. So all the planets revolve around the sun in elliptical orbits. Every elliptical orbit has two foci, and sun is situated at one of the foci of the ellipse. The other foci is blank. There is nothing there, but sun is situated at one of the foci of the elliptical orbit of all the planets. This is Kepler's first law. Now moving on to Kepler's second law. Kepler's second law states that the radius vector of a planet sweeps out equal areas in equal intervals of time. Let us understand with the help of a diagram. We see the sun as the yellow circle in the middle of the diagram, and then we see a elliptical orbit of a particular planet, and in this elliptical orbit, let us assume that on a particular day when we started our observation, the planet was at this particular location. You can follow the laser pointer. So let us assume that on one particular day when we started observing the planet was at this particular location where the laser pointer is right now. Now, if the planet is at this location, the radius vector of the planet is this one. You can follow the laser pointer. This is the radius vector of the planet. Now, after that, the planet starts to move. We keep on observing the planet day after day. And let us say after 30 days, we again make our observation and the planet has reached up to here. Now, in this interval of 30 days, the radius vector of the planet has covered an area which is shaded in blue. This is the area swept by the radius vector of the planet in a duration of 30 days. Now, after this, the planet, we stop our observation. The planet keeps on moving on its orbit. Now, when you are moving on an elliptical orbit, at some places you will be far away from the foci, which is basically the sun, and at some places you will go closer to the foci. In a circle, all the points on the circumference are equidistant from the center, but in a ellipse, the track of the ellipse sometimes goes closer to the foci, to a particular foci, and sometimes goes away from the foci. So the planet moves further and it reaches at this particular location where the laser pointer is right now on a certain day, and we start our observation again. Now we start our observation. This is the radius vector of the planet right now. The planet continues to move and we keep observing the planet for the same duration of 30 days. Now, after 30 days, we observe that the planet has reached up to this particular point. And you can see this is the radius vector of the planet now. The area which is swept by the radius vector of the planet in the same duration of 30 days is represented by this blue color sector. So you can see the two different sectors as the areas swept out by the radius vector of a planet during its two different locations in its orbit. Now, Kepler said that the area swept out by the radius vector of the planet in equal intervals of time will be equal. So the area of this blue sector will be equal to the area of this blue color sector. Both their areas are going to be same. Now, what does this tell us about the motion of the planets in its orbit? Now, if the planet has to sweep out equal areas in equal intervals of time, the planet will have to move faster in its orbit when it is closer to the sun. You see, at this particular location, the planet is much closer to the sun as compared to the previous observation. So with the planet being much closer to the sun, you see the length of the radius vector is much smaller as compared to the previous case. Now with the length of radius vector being much smaller, if it has to sweep out equal area, it has to move at a much faster pace or much faster speed in its orbit. Now, when the planet is far away from the sun in this particular condition, you can see the radius vector is very,
5 लाख
very
के हिसाब से क्या
long
रिटर्न ले रहा है ये
as
बता।
compared to the
5 लाख
radius
लगा
vector in the previous
सात
instance.
20,000 रुपया तो 7 महीने में 7 महीने चलती है माइन तो 1,40,000 रुपए उसके बाद
शिवांग तेरा
5
माइक
लाख
ऑन है।
है ना 1.5 लाख उसके बाद तू देख जैसे अपन ने किया 1.5 लाख रुपए
शिवांग तेरा माइक
दे
ऑन
मत
है।
पकड़ एक
ओके बेटा, बढ़िया है। 1.5 लाख पे बात खत्म हो गई। सो लेट्स कंटिन्यू विद केपलर सेकंड लॉ।
हाँ सर सॉरी वो गलती से ऑन हो गया था सर।
ओके, ऑल राइट, ठीक है बेटा। Now with the radius vector very, very long, if it has to sweep out equal area in equal interval of time, the radius vector of the planet has to move very slowly in this part of its orbit. So it gives us an indication that the planet moves faster when it is closer to the sun. You can see this is the sector where it is closer to the sun, and the planet has moved quite fast in its orbit. And when the planet is far away from the sun, it will move very slowly as compared to the previous instance. So the motion of the planet or the speed with which it covers its orbit is not constant or fixed. The planet keeps on changing its speed. It becomes slow when it is far away from the sun, and it gains speed, it picks up speed and becomes faster when it is closer to the sun. So this is Kepler's second law of planetary motion. The radius vector of a planet sweeps out equal areas in equal intervals of time, indicating to us that the planet will be moving faster in its orbit when it is closer to the sun, and it will be moving slower in its orbit when it is farther away from the sun. Any doubts, beta, up to here?
No, sir.
Okay.
No sir.
Great. Let's continue. Now moving on to Kepler's third law of planetary motion. Kepler's third law basically gives us the relationship between the mean distance of a planet from the sun, which is also known as its orbital radius, represented by alphabet r, and the time it takes to complete one revolution around the Sun, which is also known as its orbital period, represented by alphabet T. So the third law gives us the relationship between the orbital radius and the orbital period of a particular planet. What does the law say? The law says that the square of a planet's orbital period is proportional to the cube of the mean distance of the planet from the Sun. In other words, T square is proportional to R cube. It can be denoted in this particular relationship. T square upon R cube is constant, can be considered as K. T is the orbital period of a planet. Let's say, for example, if you take the case of the Earth. So in the case of Earth, the orbital period is 365.25 days. And R is the orbital radius, mean orbital radius of a planet. In case of Earth, the mean orbital radius of the Earth's orbit around the Sun is 93 million miles, or 93 into 10 raised to power 6 miles. So this is the relationship given by Kepler's third law of planetary motion. T square by R cube is equal to constant. This is a very important relationship, and we get numerical question based on this particular relationship. Is it clear, beta? Any doubts?
सर इसका कोई डायग्राम वगैरह है तो उसमें एक बार बता देंगे, थोड़ा सा समझ नहीं आया है।
बेटा ये टी स्क्वायर बाय आर क्यूब का,
यस सर।
इसका डायग्राम तो नहीं बनेगा बेटा. It cannot be represented in a diagram. It basically means that the time period, orbital period of a planet is related to the orbital radius of a planet. जैसे जैसे रेडियस बढ़ता जाएगा वैसे वैसे टाइम पीरियड भी बढ़ता जाएगा. Okay, and the proportional is not directly proportional. T square is proportional to R cube. So, like to give you an example, we have Mercury, Venus, Earth, Mars, all these planets. So Mercury's orbital radius is the minimum. Venus radius is greater than that. Earth's radius is even greater, and so on. So now if you compare Mercury with Earth, since the Earth's radius is bigger, the time period, orbital time period, which we call as 1 year, will also be greater in the case of Earth. Mercury will be completing its orbit in much shorter time. I think the orbital period of Mercury is about 88 days or something. So I'm not very sure about it, just a wild guess. And the orbital time period of Earth will be more than the orbital time period of Mercury. That's what it means. Did you get it, beta?
Yes, sir.
Okay, we use this relationship in our numericals. Now, when the numericals come based on the orbital time period or radius, this is what we use. So we will see that in the coming slides. Now, how can we utilize this relationship in the numerical questions? Now, for using this relationship, we need to be aware of the orbital time, or the time Earth takes to complete one orbit around the Sun, and the orbital radius of the Earth. Now, we know that the time period, orbital time period of the Earth is 365.25 days. And we know the orbital radius of the Earth is 93 million miles, which is 93 into 10 raised to power 6 miles. There is a correction, beta. ये जो 6 दिख रहा है ना आपको, this is actually superscript 10 raised to power 6. It is not 106. It is 10 raised to power 6. I don't know, I corrected it, but it is still showing wrong. And ये जो 2 और 3 पीछे लगे हुए हैं, they are also superscript raised to power 365.25 square, 93 into 10 raised to power 6 cube.
Okay, sir.
So T square upon R cube of Earth converts to 365.25 square divided by 93 into 10 raised to power 6 cube. This, being constant for each and every planet, should be equal to T square by R cube of any of the planets of the solar system. If you look carefully now in this relationship, T square by R cube of Earth is known to us. If we are given the orbital radius or the orbital time period of any of the planets, one of these two items is provided to us. By using this relationship, we can easily find out the second unknown item. If the orbital time period of a planet is given, we can put that in this relationship and we can obtain its orbital radius. And the opposite is also true. If they provide us with the orbital radius of a particular planet, we should be able to calculate the orbital time period of that particular planet. Now for this, you need to be aware of these two values, the orbital time period of the Earth, 365.25 days, and the mean orbital radius of the Earth, 93 into 10 raised to power 6 miles. These figures are not given in the question. It is expected that the candidate is aware of these figures to be used in a numerical based on the Kepler's laws. Now, next we refer to some planet configurations. Configurations basically means a particular location of the planet in its orbit. So the terms which are used to represent or show planet configurations are conjunction, number 2, opposition, and number 3, quadrature. They basically tell us about the position of a planet with respect to the sun. Let us now understand all these three configurations or all these three terms with the help of a diagram. Let's show the sun in our diagram. Then around the sun, we show planet Earth. I have shown it in blue color. Our Earth is a blue planet. And let's show the orbit of the Earth now. We have the orbit of the Earth on the diagram. Now let's show another planet of the solar system. We show the red planet, and it is the Mars planet. We are aware that the orbit of Mars is greater than the orbit of the Earth. So let's now show the orbit of the Mars. We have the orbit of the Mars in our diagram. Now, both Earth and Mars are revolving around the sun in their orbits. The speed at which they are revolving around the sun is different. They are revolving around the sun with different speeds. All the planets have different speeds. We just saw the third law of Kepler's planetary motion, which said T square by R cube is equal to constant. So as the radius keeps on increasing, the time period also keeps on increasing. So that tells us that the angular speed with which the planets revolve around the sun will also keep on changing from planet to planet. Now, with varying speed, it is possible that the Earth and a particular planet may be at different locations with respect to the sun. Like, for example, right now when you see in the diagram, you can see that for an observer on the Earth, the Sun as well as the planet Mars are in the same direction. Both the Sun and planet Mars are in the same direction. Now, this particular placement of the planet with respect to the Sun is called as conjunction. We say that this particular planet or planet Mars is in conjunction with the Sun. So this is the meaning of the first term, which is conjunction. Basically means that the planet is in the same direction as the Sun. The planet is in conjunction with the Sun. Now let's say after some time we keep on observing this particular planet, and this particular planet moves to a different placement in its orbit, and right now the planet has moved to this particular placement, this particular location in its orbit. Now for an observer on the Earth with the planet Mars at this particular location, you can see now that the Sun and the planet Mars are opposite to each other, or they are in opposite directions. The Sun is in one particular direction and the planet Mars is exactly in the opposite direction. Now this particular orientation is called as opposition. We say the planet Mars is in opposition to the Sun. So opposition basically means that that particular planet and the Sun are in totally opposite directions. Now let's assume that the planet keeps on moving in its orbit with some relative speed, and at another particular instant we observe that the planet Mars is at this particular placement or location in its orbit. Now if you observe this planet Mars carefully, you see the direction in which the planet Mars is at right angles to the direction in which the Sun is. So whenever a planet is at right angles to the direction in which the Sun is, it is called as quadrature. So this is the planet Mars in quadrature. The direction in which the planet Mars is 90 degrees away from the direction in which the Sun is. Now there is a possibility, another possibility of quadrature. If the planet Mars at a particular instant reaches to this location in the diagram, you can follow the laser pointer. So at this particular location also, the direction in which the planet is at right angles to the direction of the Sun. So it tells us that this particular planet is in quadrature with the Sun. So conjunction means the Sun and a particular planet are in the same direction, or the angle between them is 0. Opposition means that the direction in which the Sun and a particular planet are exactly opposite to each other, or the angle between the Sun and that particular planet is 180. And quadrature means that the direction in which the Sun is 90 degrees away from the direction in which the planet is, or the angle between the Sun and the planet is 90 degrees. Now these terms are important from the point of view that whenever we get numerical based on Kepler's laws of planetary motion, sometimes these concepts are used in the question. So we should be aware of what these terms means to accurately solve that particular question. So this is the importance of understanding these terms.
Beta, any doubt in any of the terms?
सर एक बात
नो सर।
बोलो बेटा।
सर ये क्वाड्रेचर एक टाइम से ज्यादा बन सकता है?
क्वाड्रेचर 2 बार बन सकता है बेटा। Like you can see, the Mars is on its quadrature twice in its orbit.
नहीं सर, 2 से ज्यादा।
2 से ज्यादा तो नहीं बन सकता बेटा।
तो सर
दूसरी साइड होएगा तो सर 2 बन जाएगा।
है ना, सो बेसिकली अर्थ पे एंगल है, अगर इनकी एंगुलर वेलोसिटी डिफरेंट है तो रिस्पेक्ट टू, अगर वो पोजीशन अर्थ के ऊपर नदरली भी हो जाए उसके रिस्पेक्ट पे, अगर मार्स प्लेनेट 90 डिग्री आ जाए तो वो भी क्वाड्रेचर होगा सर।
बेटा देखो, ऑर्बिट में कहीं पर भी अर्थ चली जाए, क्वाड्रेचर किसी भी लोकेशन पे बन सकता है, एट एनी लोकेशन। ओके, so we cannot call it a different quadrature. It can occur at any point on the Earth's orbit. Now, why I am calling two quadratures are possible, that is because you see in one of the locations, the planet Mars is to the left of the sun. If you are looking, if you have the observer on the Earth's surface, you are looking towards the sun. You see this one quadrature, the planet Mars is to the left of the sun. On this quadrature, which is on top of the diagram, the planet Mars is to the right of the sun. So ये दो possibilities हैं quadrature की. It can be on either side of the sun. But अर्थ अपने ऑर्बिट में कहीं पर भी चली जाए, वहां पे क्वाड्रेचर की पॉसिबिलिटी है।
मतलब इन 1 ईयर सर ऐसा बोल सकते हैं कि इसको कि बनेगा 2 बार भी, पर एट गिवन कहीं भी बन सकता है सर वो।
Okay, now you are trying to compare the number of quadratures in time, means how many quadratures are possible in a year, right?
करेक्ट सर।
Okay, बेटा उसका तो देखना पड़ेगा। इवन आई एम नॉट श्योर ऑफ कि एक साल में कितने क्वाड्रेचर बन सकते हैं।
सर वो तो फिर उस पर डिपेंड करेगा ना कि विद रिस्पेक्ट टू कौन से अर्थ और कौन सा प्लेनेट, अगर उसकी एंगुलर वेलोसिटी ज़्यादा है तो उसके हिसाब से तो ज़्यादा भी बन सकते हैं सर।
Certainly बेटा, it will depend upon the planet. So every planet after how much time it comes on the quadrature, वो हमें देखना पड़ेगा बेटा। This will be there certainly, but it has to be looked into.
सर जैसे अगर मरकरी की बात करें, वो अपना ऑर्बिटल पीरियड 88 डेज में कंप्लीट कर लेता है, उसमें तो ईयर के हिसाब से विद रिस्पेक्ट ज़्यादा बनने के चांसेस हैं।
Okay, hold on now बेटा, hold on. जो मरकरी है वो इंफीरियर प्लैनेट है, मीन्स उसका ऑर्बिट अर्थ के ऑर्बिट से छोटा है। तो बीइंग ए इंफीरियर प्लैनेट, मरकरी कभी भी क्वाड्रेचर पे आ ही नहीं सकता है। ट्राई टू विजुअलाइज इन दिस डायग्राम।
हाँ समझ गया सर, समझ गया।
ओके, सो मरकरी तो बेटा कभी क्वाड्रेचर पे आएगा ही नहीं। मरकरी एंड वीनस कैन नेवर कम ऑन क्वाड्रेचर। ओनली द सुपीरियर प्लैनेट्स, मीन्स देयर ऑर्बिट्स ग्रेटर देन द ऑर्बिट ऑफ द, बिगर देन द ऑर्बिट ऑफ द अर्थ, वो ही क्वाड्रेचर पे आ सकते हैं।
समझ गया सर, क्लियर सर।
ओके, एंड दैट अप्लाइज टू ऑपोजिशन ऑल्सो। ऑपोजिशन में इंफीरियर प्लैनेट्स नहीं आ सकते हैं, ओनली सुपीरियर प्लैनेट्स कैन कम इन ऑपोजिशन। ओके, और बेटा और डाउट्स? Very good. So if this is clear, then we proceed ahead.
Now, the next important concept which we have is the concept of elongation. Let's understand what elongation is. Elongation of a planet is the angle at the center of the Earth between the Sun and that particular planet. Let's try to understand it with the help of a diagram. We have the Sun in our screen now. Let's show the planet Earth. We can also mark off the orbit of planet Earth. You can see the orbit of Earth in blue color. Now let's show another planet. In this case, we show planet Venus. Now Venus is closer to the Sun as compared to the Earth. So let's now mark off the radius of the orbit of Venus also. You can see the orbit of Venus in maroon color as shown by the laser pointer. Let's now try to show the radius vector of Venus as well as Earth. So you can see this dotted line joining the center of Sun with the center of the Venus. This marks off the radius vector of planet Venus. Similarly, you can see this blue color dotted line showing the radius of the Earth. Now let's draw another line joining the center of the Earth and the center of the planet Venus. So you can see this red color line joining the center of Earth with the center of Venus. Now from this diagram we can easily understand what elongation is. You see this red highlighted angle in the diagram is what is elongation. Let's try to match with the definition of elongation. The definition says elongation of a planet is the angle at the center of the Earth. You see this red angle is being made at the center of the Earth between the Sun and the planet. So from the center of the Earth, a line joining the center of the Sun and a line joining the center of the Venus, angle between those two lines is the elongation. So angle at the center of the Earth contained between the Sun and that particular planet is known as the elongation of that particular planet. Now, as Earth and Venus are moving with different orbital speeds, different angular velocities in their orbits, their location with respect to each other will keep on changing. The planet Venus could be at any particular elongation depending upon what is its position in its orbit. Let's assume that if planet Venus is at this particular position here, the elongation will be the blue color line showing the radius of the Earth and the line joining the center of the Earth with the location of Venus at this particular point. If Venus is at this particular location here, the elongation will again be by the angle between the radius of the Earth and the line joining the center of Earth with center of the Venus. Now, if you look carefully, that as the planet Venus moves in its orbit, you can follow the laser pointer. At this particular point, Venus will be in conjunction with the Sun, or the elongation will be 0 degrees. Now, as it moves in its orbit, the elongation will start to increase. At this particular point, at the first location, it will have a certain elongation. After this, the elongation will keep on increasing. Now, if you look carefully at this particular point, Venus will have the maximum elongation. The angle at the center of Earth will be maximum at this particular placement of Venus in its orbit. As Venus moves forward in its orbit, you see the elongation will start to reduce again. Now, this point where the maximum elongation occurs, if you look carefully, you will see it is the point where from the center of Earth, if you draw a tangent to the orbit of Venus, the tangent meets the orbit of Venus at this particular point. This is the point where Venus is going to have maximum elongation. And we are aware that the tangent is always perpendicular to the radius of a circle. So this line joining the center of Earth with the center of the Venus, the red dotted line, represents a tangent, and this line joining the center of Sun with the center of Venus represents the radius of the Venus. So they will be at right angles. So this angle here at planet Venus will be 90 degrees. So this is the point of maximum elongation of Venus, and we know at the point of maximum elongation, the angle made at point Venus between the Sun and the Earth would be 90 degrees. Now this particular diagram is used in solving some of the questions.
So you should be clear about the concept of maximum elongation and what is this angle which is made at the planet at the time of maximum elongation. Now, if you consider a exterior planet means the planet whose radius is greater than the radius of the Earth, like say for example Mars. Now, the maximum elongation of Mars is going to be 180 degrees. The maximum value of elongation is possible, which it can be, is 180 degrees. For a exterior planet like Mars, it can reach up to its maximum elongation, that is 180 degrees, when it is in opposition to the Sun. But for a inferior planet like Mercury or Venus, the maximum elongation will be less than 90 degrees, and it will depend upon the radius of that particular planet and the radius of the Earth. Now, inferior planets like Venus, as you see in this diagram, can never be in opposition to the Sun. They can never be in opposition. Irrespective of whichever position they are in their orbit, they can never go in a direction which is opposite to the direction of the Sun. And at the same time, if you look carefully, you will observe that these inferior planets like Mercury and Venus can also never be in quadrature with the Sun. To be in quadrature, the angle at the center of the Earth or the elongation has to be 90 degrees, which is not possible in this particular case. So opposition and quadrature can only be attained by exterior planets whose radius is greater than the radius of the Earth. And for inferior planets like Mercury and Venus, whose radius is less than the radius of the Earth, they can never be in quadrature and in opposition.
Any doubts up to here, beta? Okay, great. So we are almost done for the session. So let's stop it here. And we will continue with this concept in the coming lecture. So now we have understood the concept. Now we will be attempting some numericals based on these. So these terms which we have seen, the elongation, basis this, there are some numericals which are asked in the exam. We are now ready to do those numericals which we'll be attempting in the next session. So that was all for this session. बेटा एक और चीज़ थी जो शेड्यूल हमने बनाया था ना, let me go to that schedule. Let me show you, just give me 1 minute. बेटा you see the schedule which we discussed. This is the one जो हमने डिस्कस किया था. अब इसमें एक चेंज आ गया है. Gupta sir actually wants to have the safety exam on Monday because he is busy later on and he will not be able to check the papers. So ये जो change है, then on Monday we will have the safety exam and navigation will then go to the Thursday, that is 11th of November. So this is the change which has come beta. बाकी exams ठीक है.
Okay, sir.
So navigation you have a choice. You want to keep on 11th, 10th, 9th, any days. Okay. So we can keep it as you require.
ठीक है सर, लास्ट में।
सर ये वाला ठीक है, इससे नेविगेशन लास्ट में।
Okay, beta. All right then. So then we will fix up this schedule. So ठीक है बेटा. That's all what I wanted to share with you. So that's all for this session. See you in the next session.
क्वेश्चंस हमें सेंड कर दीजिए, हम प्रैक्टिस कर लेंगे।
जो ये वाले हैं बेटा?
ये सर जो नेक्स्ट सेशन के लिए आप बता रहे हैं।
ओके, ऑल राइट, ठीक है, मैं भेज देता हूँ आपको।
थैंक यू
सर वो कॉक्ड हैट के भी, कॉक्ड हैट वाले सर
You asked for a cocked hat question also. Okay, cocked hat and these questions. ठीक है बेटा, डन, भेजता
और
हूँ।
स्टैगर भी बोला था सर।
स्टैगर्ड भी सर।
स्टैगर्ड के भी चाहिए। ओके ओके।
सर जो पेपर में आने वाले होगी।
सर पेपर भी भेज देना सर, क्वेश्चन पेपर भी
हाँ
भेज
सर, वो मेन है।
सर हम प्रैक्टिस कर
हाँ सर वो मेन है, वो भेज देना, वो कर लेंगे हम।
सर जो पेपर में आने वाले सारे क्वेश्चन भेज दो सर, कर लेते हैं अभी।
बेटा वो तो पेपर में ही मिलेंगे, बट व्हाई डू यू वरी बेटा? तुमने अगर इन क्वेश्चंस को प्रैक्टिस कर लिया, वंस यू हैव अंडरस्टूड दीज कॉन्सेप्ट, अब कोई भी क्वेश्चन आने दो ना, कोई दिक्कत ही नहीं है।
सर रिजल्ट अच्छा नहीं आया सर पिछला भी नेविगेशन का।
अब बेटा रिजल्ट डिपेंड्स अपॉन द हार्ड वर्क। ओके, अब मैंने हार्ड वर्क डाल दिया है अपना, अब तुम्हारा हार्ड वर्क डालने की टाइम आ गया बेटा। ओके, डोंट वरी अबाउट द रिजल्ट बेटा, रिजल्ट ठीक ही आएगा। तुम्हारे हाथ में सिर्फ एफर्ट है, सो पुट योर बेस्ट एफर्ट एंड यू विल गेट ए गुड रिजल्ट, डोंट वरी एट ऑल। ओके, ठीक है बेटा, सो देन वी कॉल ऑफ दिस सेशन एंड आई विल सी यू इन द नेक्स्ट क्लास। बाय बाय।
थैंक यू।
थैंक यू बेटा, बाय बाय, थैंक्स।